Good day, everyone. Today we are going to learn about diaphragm walls, one of the most important deep foundation and earth-retaining systems used in modern construction. As cities become more crowded, engineers often have to construct deep basements, metro stations, underground parking structures, and tunnels close to existing buildings. In such situations, conventional retaining walls may not be sufficient. A diaphragm wall provides a safe and effective solution by retaining the surrounding soil and preventing groundwater from entering the excavation. In this lecture, we will discuss the definition, applications, construction sequence, and construction process of diaphragm walls. A diaphragm wall is a reinforced concrete wall constructed below ground level using slurry trench technique, which was originally developed in Europe. In this method, a narrow and deep trench is excavated, while continuously filled with a specially prepared bentonite slurry. The slurry prevents trench walls from collapsing by exerting hydrostatic pressure against surrounding soil. Once the required depth is reached, a reinforcement cage is lowered into trench, and concrete is placed using Tremy method. Typically, diaphragm walls have a thickness ranging from 300 mm to 1,200 mm, and can be constructed to depths of about 45 meters. Because the wall is cast directly in ground, it serves as both a retaining wall and, in many cases, a permanent structural foundation wall. Diaphragm walls have a wide range of applications in civil engineering. They are commonly used as permanent retaining walls for deep excavations, foundation walls for high-rise buildings, structural elements in top-down construction, where the superstructure and basement are constructed simultaneously, groundwater cutoff walls to prevent water seepage, seepage barriers in reservoirs, dams, and canals, retaining systems for metro stations and underground tunnels. One major advantage is that diaphragm walls can be constructed very close to existing buildings, with minimal ground movement, making them highly suitable for congested urban areas. Diaphragm walls are particularly effective in soft clay, loose sand, and other weak soils below the groundwater table. In such conditions, excavation without support may lead to soil collapse or excessive settlement. By using bentonite slurry during excavation, the trench remains stable until the concrete is placed. Therefore, diaphragm walls are widely used whenever there is a need to control lateral soil movement and groundwater during deep excavations. Let us now understand the construction sequence. The first step is the construction of guide walls. Guide walls are shallow reinforced concrete beams constructed on either side of the proposed wall alignment. They guide the excavation equipment and ensure correct positioning. Next, trench excavation is carried out using specialized equipments. During excavation, bentonite slurry is continuously circulated to balance the lateral earth pressure and prevent trench collapse. After reaching the required depth, stop-end pipes are installed at both ends of the panel to create construction joints for adjacent panels. The reinforcement cage is then carefully lowered into the slurry-filled trench. Finally, concrete is placed using the Tremy method, displacing the bentonite slurry upward. This slide shows a hydrophrase drilling machine, one of the advanced machines used for diaphragm wall construction. Unlike conventional grab excavators, the hydrophrase uses rotating cutter wheels to excavate hard soil and weathered rock with high accuracy. The excavated material is transported to the surface through slurry circulation. This equipment allows engineers to construct deeper and more vertical diaphragm walls with excellent quality and dimensional accuracy. The construction begins with excavating primary panels, usually having lengths of 4 to 6 meters. After excavation, stop-end pipes are placed vertically at both ends of the panel to form proper joints with the adjacent panels. Once excavation is complete, a prefabricated steel reinforcement cage is lowered into the center of the trench using cranes. This reinforcement provides the structural strength required to resist earth pressure and bending moments. Concrete placement is carried out using the Tremy method. Concrete with a slump of 150 to 190 millimeters is poured through Tremy pipes that extend to the bottom of the trench. The concrete is placed continuously without interruption. As fresh concrete rises from the bottom, it gradually displaces the bentonite slurry upward. An important point is that the lower end of the Tremy pipe must always remain embedded in fresh concrete to prevent mixing of concrete with slurry, ensuring high-quality construction. Concrete placement continues until good quality concrete reaches approximately 300 millimeters above the final cutoff level. This extra concrete is later removed during finishing. The displaced bentonite slurry is collected, cleaned, and reused for excavating the next panel, making the process economical. Depending on excavation depth, the completed diaphragm wall may be supported using ground anchors, struts, or props to resist lateral earth pressure during excavation. This figure summarizes the complete diaphragm wall construction process. You can observe the sequence beginning from trench excavation, slurry stabilization, reinforcement placement, Tremy concreting, and finally the completed reinforced concrete wall. Each stage must be executed carefully, because any interruption during concreting or improper slurry management can affect the quality and water tightness of the wall. To conclude, a diaphragm wall is one of the most reliable deep retaining systems used in modern civil engineering. It provides excellent structural strength, controls groundwater, minimizes ground settlement, and enables safe excavation in congested urban areas. Today, diaphragm walls are extensively used in metro rail projects, underground parking structures, deep basements, tunnels, dams, and other major infrastructure developments. As future civil engineers, understanding this technology is essential because it plays a significant role in modern underground construction. Thank you.